realize that if you are talking about any particular chemical reaction in our body, some reactions would occur, they are possible from thermodynamical point of view, and we will talk about this today, but without an enzyme, it would take forever. Okay, it would take your whole life, to have a particular reaction. We cannot wait that long. So here, if this is, we are looking at the kinetics of the reaction, on the x-axis, you have time. On y, we are looking at the product that is formed by the chemical reaction. And without the enzyme, it would take hours, or maybe even longer, or days, or months, or even years. In the presence of the enzyme, you have reaction occurring in seconds, or milliseconds, so below a second. And this is what enzymes do. They are catalysts. So as really one example here, you have the cleavage of peptide bond. You remember this. This is a primary sequence, primary structure of a protein. So this is a short peptide, and we have a peptide bond right there. That bond may actually be hydrolyzed, so you need water molecule in the presence of water. Everything is in the presence of water, right? Our life takes place in the presence of water. You could have hydrolysis of that bond, and you could break this bond, and you could have 2 amino acids. This is very inefficient and would take incredibly long time without an enzyme. We have a class of enzymes that are called proteases. What proteases do? They cleave peptide bonds with the help of water. They speed up this reaction. I should say it correctly. So one example. Here you have more examples of how those enzymes work, and really don't bother about the names because you don't know what those names are, what the reactions are. But what you see here is the rate of the uncatalyzed reaction, so how long it would take without an enzyme, how fast this reaction proceeds in the presence of the enzyme. Now, this is K. K is a rate constant, uncatalyzed per second. Catalyzed rate per second. Why per second? This is a speed. When you drive your car, the speed is measured in how fast you go, miles per hour, right? So here is per second, how fast this reaction goes. Uncatalyzed, catalyzed. Rate enhancement is you take this number in the presence of the enzyme, divide by this number, Wednesday. You take this number, divide by this number, and you get rate enhancement. So you have to take this, divide by this, take this, divide by this, and you have rate enhancement. Look, the slowest example, the enzyme that is actually gives you the lowest rate enhancement on this list, enhances million times. The enzyme on the top of this list, 10 to the 17th. Okay, this is a huge rate enhancement. We are not talking 2, 3, 4, 10 times. We are talking millions, and really orders of magnitude even much larger. So this is absolutely huge effect. Most enzymes are proteins. So this is now good time to talk about enzymes because we just talked about proteins. I say most. What does it mean? 99 point, again, I don't know exact estimate. 99% of all enzymes are proteins. There are exceptions from those rules. For example, ribonucleic acids can sometimes act as catalysts. Okay, so there will be many things we'll talk about today. Classes of enzymes. I showed you that one example, proteases, that were cleaving a peptide bond. But here we will list several classes of enzymes, and this is At this point, we are moving ahead of ourselves because we did not talk about metabolism and different chemical reactions that take place in cells, and I'm already giving you names of the enzymes. But that's okay. That is just one slide. So, for example, a lot of reactions in living systems deal with moving of electrons between molecules, okay? So, electron transfer between two molecules, those are oxidation and reduction reactions, and the enzymes that catalyze those are called oxidoreductases. Remember we said disulfide bond between two cysteine residues can be reduced. Well, you can form first disulfide bond between two SH groups, so this is oxidation. You can convert it back to two SH bonds to two SH groups, so hydryl, this would be reduction. So oxidoreductases. Now, transferases, transfer of functional group from one molecule to another, such as phosphate group. We said 3 amino acids, serine, threonine, tyrosine, can be phosphorylated in proteins, right? This was, don't remember if this was on the exam, it was in the study section. So, what does it mean, phosphorylation? You are moving phosphate group from one molecule, ATP, to amino acids. So this is transfer. You can move glucose, sugar, from one molecule to another. So transferases. Hydrolases catalyze cleavage of molecules driven by addition of water, such as proteases. So proteases are actually a subclass of hydrolases. You cleave a covalent bond, but you need water. This is why it is hydro, okay, hydrolases. Lyases, you will not see those very often. Those are more specialized, catalyze addition of atoms or groups to a double bond. So if you have a double bond and you are adding some groups there, then those are lyases. Isomerases, very common and important, catalyze transfer of functional groups within a molecule. So they create different isomers of the same molecule. Remember, aldehyde, the best example, aldehydes and ketones. Again, I wanted you to remember for the exam those functional groups. Aldehyde, C double bond oxygen, H. Aldehyde, or you can have C double bond oxygen carbonyl group somewhere in the middle of the protein. One of those groups is not hydrogen. If you count the atoms, if you write the formula for that molecule, aldehydes and ketones will have the same formula, but again, carbonyl group in one case is at the end of the molecule, COH, or in the other one in the middle, in ketones. So isomerases, isomerization, two different isoforms. Ligases catalyze the link of two molecules into a larger one. Come on, if we are really building, if we are making, some big sugars or something from scratch, you have to take two parts, small parts, and you have to bring them together. So those are called by, those reactions are catalyzed by ligases. For example, during DNA cloning, we have two pieces of DNA, you join them together, you create a DNA that will be coding a new molecule, new protein, and those are ligases. So this class is called, those are called ligases. Okay, now this is the very important part. Thermodynamics versus kinetics of enzymatic reactions. So let's consider a very simple chemical reaction. Substrate is converted to product. So reagents before the reaction took place are called substrates. What you are forming is a product of chemical reaction. So the simplest one substrate is converted to one product molecule. You could have several substrates, several products. You will see those, but this is now the simplest. Okay, and thermodynamics is thinking about energy change. So I have to describe what is the free energy change for this reaction. So free energy we designate with G, delta, capital Greek letter delta, change of this reaction. So how is it defined? Delta G is the final energy. So G, free energy of a product, minus what I had at the beginning, free energy of the substrate. So this is delta G. This is the fact that is absolutely true for living organisms, for chemical reactions in general. If you want to conduct them in a tube, reaction will take place spontaneously. Spontaneously, we are saying, will substrate be converted to product? Spontaneously, if delta G is less than 0. This reaction cannot take place, regardless of the enzyme, presence or not, cannot take place if delta G is greater than 0. And this reaction, we call it is at equilibrium if delta G is 0. So you have those three situations: equilibrium, spontaneously, delta G, reaction taking place spontaneously if delta G is less than 0, and cannot take place if delta G is greater than 0. Now, if you have a particular reaction, and if you determine that delta G is less than 0, so you would say, okay, this reaction will take place spontaneously. From delta G, from thermodynamics, you have no clue how fast this reaction will take place. All what you can tell based on the value of delta G is whether this reaction will or will not take place. You have no idea how fast this would take place. So delta G does not provide you any information about the rate of the reaction. Okay, so this is the good diagram, because this is the energy diagram where we have on y-axis that free energy, G. So free energy, G. You can put a G there, capital G. What is on x-axis? They say reaction progress. And you are asking, what is the reaction progress? In a sense, you can think about this as time. Okay, so time. For our purpose, thinking about time is correct. But in general, they draw a reaction progress here. And now we are starting with a substrate, and you are converting it. With the longer you wait, everything is converted to product. This reaction will take place spontaneously because this is the delta G, the difference, final G minus the initial of the substrate, product minus substrate. Of course, the energy of the product is lower than the energy of the substrate, so delta G is less than 0 for this reaction. Do we agree? Delta G is less than 0. Do we agree? Do we agree? Okay, so this reaction will take place, will occur spontaneously. Okay, but I will come back to this graph in a second. Now let's think about G or delta G in a different way. So if we consider a reaction now like this, two substrates A and B are converted into two products C and D. Delta G for this reaction, in practical terms, I can write it this way. I can write it down this way. Delta G equals delta G0 prime, which is the standard free energy change. And this is a constant for a given reaction. So if you think about whatever reaction, hydrolysis of ATP, whatever, this is constant for a given reaction. You can Google it, you can find it in a textbook what delta G0 prime for this reaction is. Plus, we have additional term, RT, natural logarithm, not decimal logarithm as it was in the case of pH or Henderson-Hasselbalch equation, natural logarithm of the ratio of the concentrations of the products, C times concentration of product D, divided by concentration of substrate A times concentration of substrate B. Okay? So what is, first of all, what does it mean standard free energy change? So we have to define that standard state, and the definition, which is, really have to take it, we will be not dwelling on this too much. All the reactants are at 1 molar concentration. Temperature is 298 kelvins, which corresponds to 25 degrees centigrade. And because we are talking about living systems, which take place in cells, in buffered environment, we have to provide pH. So pH is 7, which is neutral. Okay. First comment about pH. So pH 7 is neutral, it's good, but there are issues with pH 7 because many times in some reactions protons participate. And as you know, concentration of protons at pH 7 is 10 to negative 7 molar. Weird number. Not really useful, not very helpful, to use it in all calculations. So biochemists agree that when pH is equal 7, we will, for the purpose of this, when we calculate the delta G, we will use the value 1 for concentration of protons. Okay, so I know this doesn't make sense because you would say, wait a minute, I tortured you to remember that at pH 7, concentration of protons is 10 to negative 7 molar. For this particular purpose, we can assume that then we take it as a 1, rather than writing 10 to negative 7. Now, water participates many times in the reaction, like as, for example, when a reaction is catalyzed by hydrolysis. Concentration of water, I think in the second lecture we calculated how much it is, 55.5 molar. And doesn't change because it's such a huge concentration, doesn't change much when water is taking part in the reaction. Again, for simplicity, we don't want to write everywhere and multiply everything by 55.5, so we will take concentration of water as 1. Okay, now temperature. No Fahrenheit whatsoever. So first of all, everything that biochemists do, all the temperatures, we have to write down protocols for some procedures that we do in the lab, is in Celsius. Okay, so every student, undergrad, graduate student, everybody is used, every biochemist to use centigrade scale. Okay. Now, for the purpose of thermodynamics, even this is not enough. We have to convert it to kelvins, which is whatever you have in centigrade plus 273. And this gives you the temperature in kelvins. So you see 25 plus 273 is 298 kelvins. So this is a definition of the standard conditions. What is R is a gas constant, and T is the absolute temperature in kelvins, as I said, which is here, you are converting from Celsius to Kelvin. I will not be asking to calculate delta G, so you don't need to deal with those R and T's and so on, but for the record, we have to list it here. What is more important, okay, is now consider, again, how those delta G's relate to whether reaction will occur spontaneously or not. So let's consider equilibrium. reaction is in equilibrium, delta G equals 0. So I can, in my equation, delta G equals delta G0 prime plus RT natural logarithm of the ratio of the concentrations. I put 0. If it is 0, then delta G0 prime equals negative natural logarithm of those concentration ratios. Because we are talking about equilibrium when delta G is equal 0, those concentrations, I will put a subscript on them and will indicate that those are equilibrium concentrations. Now, I can define equilibrium constant as this ratio, okay? So C times D divided by concentration of A and B at the equilibrium. This is my equilibrium constant. Definition. If so, delta G0 prime equals negative RT, natural logarithm of the equilibrium constant. Prime because it is at the pH 7. So, in other words, I said delta G0 prime is constant for a particular chemical reaction. Why? Because you can always calculate delta G0 prime from equilibrium constant. And equilibrium constant, if you know delta G0 prime, you can this is just exponential function, right? So exponents of negative delta G0 prime divided by RT gives you equilibrium constant. So those values, delta G0 prime, K equilibrium, are, as I said, you can easily find them anywhere. Textbooks, internet, they are provided, they are known for common reactions, for all actually known reactions that take place in living cells. Okay. So the values of equilibrium constant and delta G0 prime are related, okay? Now, let's look at this equation. Whether the reaction occurs spontaneously or not depends on, you have to know delta G0 prime. And this is not enough, you need to know the actual concentrations of A, B, C, and D. And they are, in general, they are not equilibrium concentrations. That can be anything. So, in other words, if I give you some numbers, and if I say you are dealing with a reaction for which delta G0 prime is negative 10 kilojoules per mole. Delta G0 prime is negative 10 kilojoules per mole. Can this reaction occur spontaneously or not? Can you tell me, based on this information that I gave you, delta G0 prime is negative 10 kilojoules per mole? Nothing else. I'm not telling you anything else. I'm just giving you delta G0 prime. Can you tell whether this reaction occurs or not spontaneously? You can't, because you don't have enough information. Delta G0 prime, so pay attention on Wednesday. Pay attention to what numbers you are given. If I tell you delta G0 prime is plus 20 kilojoules per mole, can this reaction occur spontaneously or not? You don't know. If I give you delta G0 prime and I give you concentration of C and D, but I still do not tell you about A or B, you still cannot tell, because you need to know delta G0 prime, concentration of C, concentration of D, A, and B. If you do not have all this full set of numbers, you cannot tell delta G. By the way, I will not ask you to calculate delta G and take RT natural logarithm. I just want you to assess, whether it can or cannot occur spontaneously. Now, enzymes, and this is absolutely key fact, cannot alter the equilibrium of the reaction. So enzymes do not make the reaction happen if delta G is greater than 0. As we said, thermodynamics dictates and tells us that if delta G is greater than 0, reaction will occur spontaneously. And you may add your enzyme. You may add the enzyme, and this is not a magic little person that will make the reaction happen, enzyme. If delta G is greater than 0, enzyme cannot do anything. If delta G is less than 0, reaction will occur spontaneously, but without the enzyme, maybe it would take hours. And in the presence of enzymes, it will go faster. Why? So once again, we are looking at this energy diagram, and like this, in this case, we said delta G is less than 0, so this reaction will occur spontaneously. The substrate will be happy to go down, to be converted into the product, but there is a hill to go through, to climb for a substrate before it is converted to product. And this point on this energy diagram is called transition state. It is here depicted with X, double dagger, whatever. So indeed, substrate, before it is converted into product, has to be converted into this transition state. And we have to go uphill before you go downhill. So what is that, first of all, transition state? Is no longer substrate, but it's not a product yet. Something in between, okay? So it doesn't look like a substrate, but it's not a product yet. So this is a transition state. And look what enzymes are doing. Enzymes are decreasing the energy of the free energy of the transition state. So in the absence of the enzyme, when the reaction was uncatalyzed, the substrate had to climb a very high hill, transition state, and then to be converted into product. And in the presence of the enzyme, that hill is much, much lower. If you get anything lower and on the free energy diagram, we call it stabilization. So we say that the transition state is stabilized. What enzymes are doing is they are stabilizing the transition state. What is the difference between this energy of the transition state and the substrate? It is called activation energy. So enzymes are decreasing the activation energy. They are decreasing that hill that the substrate has to climb over. So the enzymes function to lower the activation energy, and the enzymes facilitate the formation of the transition state. As I'm saying this, you can say it also, phrase it, that they are stabilized transition state. So the essence of enzymatic catalysis is stabilization of the transition state or decrease of the activation energy. I'm just realizing, this is important, the blue bullet. I'm looking for definition of activation energy. Activation energy, this is that activation energy, is the difference in free energy between the transition state and the substrate. Transition state of the substrate. And enzymes decrease activation energy, or you may say stabilize transition state or facilitate the formation of the transition state. If you really don't have anything better to do, just staring at the slides from this presentation, this is the slide you should start at, okay? So, because this really includes the essence of what enzymes do. Okay, now how do they do it? How do they stabilize the transition state, you may say. Well, yes, in a second we will say this, but we have to introduce then a term of active site. So, as I said, most of the enzymes are proteins. So here you have that tertiary structure of a protein, and at the bottom you have a primary structure or sequence from N to C terminus. And what this slide is showing you, that when you look at the properly folded protein, active site is indicated with this orange dashed line, and it is actually the place in the protein where the substrate would bind. Substrate does not bind randomly. It will always, in every molecule of the enzyme, substrate will bind in some cavity, maybe here as shown and as indicated by those colored side chains in amino acids. So special amino acids, when protein folds, form that cavity or the active site where substrate would bind and will be converted into product. By the way, if you really look at the primary sequence of the protein, those colored amino acids could be very far away from each other. In this particular case, let's say that this protein had 129 amino acids, and those colored ones are 35, 52, 62, and 3, and 101, 108. This is really an example. So they are incredibly far in the primary structure, and they come close, much closer to each other when the protein folds. This is why, primary structure, of course, we have to deal with it. We need that. But if you are looking at this, if you were really looking at 129 amino acids, you would never guess that after folding, those would come close together, and this is where the active site would actually, form. So active site is a very important term for an enzyme, because this is where the substrate binds and is converted to product. So for example, you can think about enzyme, yellow, and a substrate, green, that will try to bind to it, right? And in this diagram, you have like that 3-point attachment. This sharp end of the substrate would fit to that side, A, B, C. And many times, or long time ago, before people really realized how enzymes work, they thought about this as a kind of complex that is being formed between substrate and an enzyme, as a perfect fit. So they thought, okay, so if this enzyme is going to convert this substrate into product, you have to have that perfect fit. And in this case, as I said, there's 3-point contact. It doesn't have to be, of course, this way. But so this is, you might have heard the term that the substrate fits to an enzyme like a key to a lock, right? To open the lock, you have to have a key, and that fit has to be perfect. It turns out that this model, or this way of thinking about this system, is not very good and is actually not accurate. That perfect fit, like a key to a lock, would not actually be good for this enzymatic reaction. So the real situation is more like induced fit. So you should think about induced fit. So substrate actually does not fit, as you see, perfectly to an empty enzyme. When you form that complex, enzyme substrate complex, there is some adjustment. And here it looks more like the enzyme is adjusting to the substrate, right? So we have that induced fit. But the truth is that the substrate is adjusting also a little bit. So both two guys are adjusting to each other. And there is some, some strain that is, that the substrate is experiencing where it binds to the enzyme. So the structure of the active site of an enzyme may be the most complementary to the structure of transition state. So this is why we are talking about transition state. As I said, substrate, when it is going to be converted to product, it will first become transition state. And enzyme may be most complementary to the transition state. So this is why I say substrate is changing the enzyme. Enzyme is changing the substrate into transition state. And transition state is at the very top of the energy diagram, incredibly inconvenient position to be at. You know, at the top of energy diagram, all molecules want to go down and want to always minimize energy. Okay, so here is a busy example, intimidating example, I agree, but let's just look at it. You have proline, one amino acid, L-proline. As you know, all amino acids are L, so this is L, this is our alpha carbon, and we are converting it to D-proline. Very unusual, I don't know why that such an exotic example is given here. But anyway, we are converting L-proline to D-proline, so position of the hydrogen of alpha carbon, look, here it was behind the plane of the screen, here it is facing in your face. Alpha carbon is tetrahedral, so it's not flat, as you know, so H is either behind the screen or towards you. So we are changing its position. But to change from here, from L to D, the transition state looks like this. So we are abandoning that proton for a second. We have the planar structure, okay, flat, and then we are taking back proton, but when it is taken back, it is facing towards you. So this is a transition state, okay? And if you take a molecule that are analogs of transition state, they are very potent enzyme inhibitors. We will talk a lot about inhibition and all kind of enzyme inhibitors on Friday. On Wednesday, we will talk about enzyme kinetics. Today is more about thermodynamics. We will talk about kinetics on a lot of calculations actually on Wednesday, and on Friday we will talk about inhibitors. So molecules that look a little bit like transition state. So the transition state was planar structure, flat, and this is not transition state, but it is, because you look at, you know, we have double bonds here in this ring. This is not the same molecule, but it is definitely reminiscent, right, of this transition state. So this would be a very good inhibitor for the enzyme that catalyzes the reaction. Transition states are very rare and very unstable molecules, so it is not typically possible to isolate transition state. But you could use molecules that are analogs, that resemble transition states, and they are good inhibitors. Okay, so the molecule on the right mimics, this one mimics the structure of the transition state, so it is a good inhibitor. Now, some general simple properties at the end of the enzymes. So enzymes, because they are protein, they have special features. So typically, when you have the reaction in a test tube and you increase the temperature, the enzyme activity is increasing. If you look at something at 4 degrees centigrade versus room temperature 25 degrees, typically at 25, the enzyme will be working faster. Why? Because of those Brownian motions in the solution, it's a greater chance for the enzyme to see, to experience, to encounter substrate. They can meet easier because all molecules are moving faster when you increase temperature. Okay, but when you increase and increase and increase, hola hola, your enzyme will be denatured. This is the enzyme that is a protein, and high temperature, when you when you cook whatever, when you cook an egg, look like, you know how a raw egg looks like and how after you cook it. And this is irreversible, or you make scrambled egg, whatever you like. You cannot reverse that process. This is irreversible denaturation. We talked about denaturation using those urea and guanidinium hydrochloride, remember? Denaturation, those molecules acted as denaturants because they were breaking hydrogen bonds that were stabilizing proteins. Temperature, thermal energy is doing the same. You are just breaking everything, all those hydrogen bonds apart, and you are denaturing the protein, and this is an irreversible process. So enzymatic activity would usually increase with the temperature, but at certain point when the protein is denatured, depends on the protein which temperature this would be. But typically is around, I would say, 40, 50, definitely 60 degrees Celsius. So the activity goes down. Now, activity depends on pH. So if you look at enzymatic activity, and this is pH scale, well, here from 0 to 11, typically you get a bell-shaped curve. So there is an optimal pH. So this is an enzyme that is called chymotrypsin, that actually is one of those proteases that would cleave peptide bond. And chymotrypsin is involved in digestion. When you eat, you know, your proteins that you ate have to be broken down completely. So peptide bonds have to be hydrolyzed. In the upper intestine, where pH is roughly neutral, chymotrypsin is the enzyme that is doing most of the job. And look, its activity is actually high, around 7 or even 8. Now, if you increase pH or decrease pH, enzyme activity will go down dramatically. Again, because those pH values will denature the protein. Okay, in our stomach, as you may know, pH is incredibly low. And it is approximately 2, 2.6 in the stomach. And we still have enzymes that are chewing your peptides into individual amino acids. An example is pepsin that is operating in the stomach. And this one evolved in such a way that actually good for us, fortunate for us, its maximum activity, it is approximately at pH 2. So that is good. Pepsin can actually work. This is a very unusual, I have to say, enzyme, because most of the enzymes have actually optimal pH around neutral. Pepsin in our stomach, its pH, optimal pH is very acidic at pH around 2. Okay, but typically the point is that whatever enzyme you take, and if you went to the lab and if you did this experiment and if you were measuring enzymatic activity and if you were changing pH, you would see a bell-shaped curve, and most of the enzymes will have optimal activity at neutral pH. And finally, many enzymes, which are proteins, they need some help. So they need cofactors. They bind some molecules very tightly that are called cofactors, and they help actually the enzyme to perform catalysis. Without those cofactors, the enzyme's protein would not be able to do its job, catalyze a reaction. So what are those cofactors? Some small organic molecules or maybe metal ions. And the question is, does every enzyme need a cofactor? Absolutely not. And there are many enzymes that do not need any cofactors. But there are some enzymes that need cofactors. Some vitamins may actually work as cofactors for some enzymes. So if you have an enzyme that requires cofactor and you do not provide the cofactor, then the enzyme is called the apoenzyme, which is an empty enzyme or enzyme without a cofactor. When you provide a cofactor, the enzyme is called a holoenzyme. It is the enzyme with a cofactor. And the final slide, really examples of those cofactors. Sometimes they are called coenzymes. Biotin is one of the type of the vitamin. And you have metal ions, all kind of metals, zinc, very popular, magnesium, molybdenum, selenium, and so on. So, remember this, kinetics on Wednesday, and on Wednesday at noon, the quiz number 3 will open, and on the quiz we will have this material and from Wednesday, and I will post the results of the exam as